So we're going to discuss the capturing of agent dynamics within discrete space. We noted that with AnyLogic, there are basically three abstractions of space supported. Continuous space, which we've just seen, in which we've just seen mobility exhibited, both in a more abstract sense and in a sense for a set of institutions. Secondly, GIS space, where each individual is associated with latitude, longitude, heading, and geographic context. And thirdly, a discrete space. And we're going to take a look at that last element of discrete space. And we have a model here, which is a close variant of a classic model called the Schelling Segregation Model, which exhibited, which first was explored in the 1970s by I believe it's Thomas Schelling, a sociologist, in exploring the emergence of segregation in neighborhoods. There's in order to explain this model and our variant of it, it's worth noting that in addition to supporting multiple space types, AnyLogic also supports two basic models of time. And one of them, time is continuous, and this is the one we've explored most. Here, every agent is updated at a different time. And you could describe it as continuous, but also asynchronous. There's different points at which different agents are updated in continuous time, and no two agents are likely to be updated exactly the same time during model execution, or it's more rare. So essentially, agent-related incidents or events happen at arbitrarily spaced times, and continuous time is used to broker between competing risks. So if there's a competing risk between death and development of end-stage renal disease among diabetics, whichever happens first will happen first in our model. Which just by happenstance, if one occurs before the other, that will occur first. There's an alternative way of representing time, which is very traditional within agent-based models, and this is a lockstep approach where time is separated into fixed time steps. They're also called ticks sometimes. And this involves sort of a discretized time where after some period of time, all agents are updated at once. And there you have to explicitly broker between competing events. If there's competing risks associated with an agent, say competing risk associated with death and development of end-stage renal disease, both could have occurred during that time, and you have to figure out sort of which takes priority, which is the one that is applied. Did the person die before they developed end-stage renal disease or not? Because you're dealing with, say, the past year. And you've got to figure out, okay, which occurred first and broker between them. And this makes it a little bit more cumbersome, but it's a very common mechanism. Another issue that has to be brokered is if agents want competing resources, which are the ones that actually get it. For example, if two agents want to move to the same location within the same year, which of them that gets it first? Traditionally, agent-based models have been described predominantly in a discrete time fashion, but it does raise some complexities, some complications. In this case, we work mostly in continuous time. But there are a number of models that ship with AnyLogic that use discrete time. And to help illustrate this, I'm going to load into AnyLogic right now one of the help menus. So if you go AnyLogic Help, and specifically you go to Example Models, you should come up with a splash screen. And down on the right-hand side, there's a model. So this is, I think, shown in the default example. There's a model that says Schelling Segregation, and I'd like you to open it, okay? The Schelling Segregation Model is depicted here, but it itself is a variant to the original, but it does capture the fact the time is discretized in the original model. Thomas Schelling originally played this model on a checkers board using pennies to represent people of different groups. And individuals who are scattered in a discretized space, these different squares, such that in any space you had either an empty square, a square of a red color, or a square well, here depicted as red, square of one group or square of a different group. So it's a given square is occupied by either a person of one group, another group, or empty. And here we exhibit the evolution of this system over time in the context of preferences. The model's actually running right now. No one's moving because no one sees fit to. But if you run the model forward, you'll see additional movement. Let's go see a little bit about how this is implemented in AnyLogic for this particular version. Here we have a main space. Agents are arranged in a grid. Anyone remember how we can arrange agents in a grid? Where would we specify that? Yeah, it's in discrete cells, and who specifies it's in main, right? They're arranged here in discrete space with 100 columns, 100 rows, and here we have agents scattered randomly among those locations. So among the available locations, they're scattered, okay? And the number of people in the state is 8,000, okay? 8,000 total in this space. And here you could see it picking either red or black with a certain randomness. So we have 8,000 people in a space which is of size 10,000. That is 100 by 100. So there's 20% of the cells are unoccupied. Each individual is arranged in a certain neighborhood. Here's a Moore neighborhood, which means 8 neighbors. We could use an Euclidean neighborhood. Okay. So these individuals are scattered throughout the cells in this space. Now, what's notable is that when a person goes to move, or when it is how the evolution occurs. So this is the basic logic of it. And I recognize that not all of you are interested in the details of such logic, but the basic deal is we have time divided into fixed time steps. So this is the Lockstep model of discrete time. Things are occurring at certain fixed ticks. And this is supported in AnyLogic by defining these events called on-before step and on-step. Dividing things up into these two fashions allow us to avoid depending on the vagaries of which agent gets updated before which agent, and having that skew things. Because something which occurs in some traditional agent-based modeling frameworks is if you have all these agents, the one that's updated first in a given time tick, that agent's updated state is seen by the others to consider what they're going to do. So here, what we do is we divide up time into these steps, these ticks, but just before a step takes place, all the agents gather the information needed to actually decide what they're going to do. Before any agent has been updated, the agents figure out what they're going to do. In this case, they figure out if they're satisfied or not. That's the information they need to determine based on other agents. And then, at the time of the step, if they're not satisfied and they flip a coin, then they'll jump to an empty cell. So before anyone makes a change, they gather all the information they need, which is here whether or not they're satisfied. Okay? So what's going on here? Well, at this time, to determine whether or not they're satisfied, they go through each of their neighbors, they get their neighbors, and they're going to count up the numbers that are the same color as them. If they have no neighbors, they're viewed as satisfied. Otherwise, for each neighbor, if that neighbor's color is equal to their own color, they count it as being being increment the count of neighbors that are the same colors themselves. And then they're viewed as satisfied if the number of those with the same color is greater than a certain sort of tolerance threshold times the number of neighbors. Okay, so there's a threshold we set through the interface, which basically specifies our degree of tolerance for neighbors of a different color. And if that tolerance is low, actually this threshold I think specifies intolerance. Okay, so right. So if this number of the same right, so this is our degree of intolerance. So the bigger the threshold is, the more neighbors we'll need of our same color to be satisfied. So this threshold up at the top that we run here when we run the model, this preference to have neighbors of the same color. It's sort of a measure of a degree of intolerance, wanting people of only the same color. The lower it is, the less segregation we'll tend to get. The higher it is, the more pronounced the segregation patterns seen visually. And as it grows, the segregation patterns grow larger and larger until at some point no agent's going to be satisfied. Okay, so this is a Schelling segregation model as depicted in AnyLogic. It's not quite the exact same as the original model, but I want to draw some features to you. The most important feature I want to emphasize is this one here, jump to empty cell. Here, an agent that's dissatisfied and is going to move jumps to a randomly chosen cell that's empty, that has no current occupant right now. They jump to a cell that has no one in it, and that means that they'll be in a neighborhood where their preferences may be satisfied in this new neighborhood, but they jump to a neighborhood in a blind fashion, fundamentally. So there they jump to this new neighborhood, and in that new neighborhood, they'll re-examine the situation in the next time step. So within this Schelling segregation model, this is the key element of mobility. We have agents as defined by persons. Each person has a color and an indication of whether or not they're satisfied. Now, in this other model I've given you, it's kind of a continuous time representation of this. So here, they're in a state chart, and in the state chart, they periodically examine at a rate of 1 whether or not they're satisfied or not. And we allow the scheduler to broker who goes first. This is a rate of 1. Some people will re-examine it sooner than others. And based on the outcome, based on whether we're satisfied, is determined by this satisfied function. If is satisfied is true, we remain in place. Otherwise, we jump to a random empty cell. Similar logic, but in continuous time. So you can use discrete time and discrete space together, or you could use continuous time and distinction. This Schelling segregation model we saw up here makes use of both discrete space and discrete time. It's discrete space because if we scroll down, we'll see space divided into columns and rows. It's discrete, and people are also updated on a discrete time basis in this lockstep way at these fixed ticks. They're updated together. By contrast, this other Schelling segregation model, we have a representation in continuous time. We don't have to worry about updating everyone together, and we can make use, therefore, of state charts quite easily. And if they're satisfied, they stay here. If they're dissatisfied, they move. This jump to random empty cell is the same basic mechanism we used up here, jump to random empty cell, to move to an empty cell in the board. Now, in discrete space, there's a different set of a different set of features than there are in continuous space, and we'll be discussing them. One thing I want to highlight, though, is a missing component of what we've mentioned here. If we go down, and I think in AnyLogic it's still here, you'll notice that the Schelling segregation model enables steps. What this means is that, at every one time unit, it will be executing that step that we saw here for the person. This step where the person's state is updated. All the person's states are updated at the same time. So all the agents have this invoked just before this is invoked. So if you wish to invoke discrete time, you can do so here. If you wish to invoke discrete space, you can do so here. Okay? This other model shows a continuous time model with discrete space. So if we look at this other model, the continuous time Schelling segregation model variant, there's no steps enabled. Yeah. Yeah.
That means that you don't necessarily have to have a common time, like reduce your time to the smallest
Correct.
space, because if your different populations can have different time steps.
Different time scales, for example, associated with them. Continuous time is generally more flexible for a couple reasons. It's easier to deal with because a lot of things that you would have to deal with explicitly, namely trying to figure out which of competing risks actually occur first within a given year. So in discrete time, you're processing, say, a year at a time. And there are these risks that apply for that year. And if you want to have a historic record of sort of how many cases of end-stage renal disease there were versus how many deaths, you've got to figure out, okay, for a given person, both risks applied. Suppose by the luck of the die, they died during that year and they developed end-stage renal disease, which occurred first. And you've got to impose that as your competing risk. Whereas within this context, with a continuous time context, that's automatically brokered. Whichever occurs first is the one that is recorded as occurring first. There's less unpacking you have to do on these times when you're actually handling things. The fact that the events are in continuous time lends greater ease of sort of describing the dynamics over time. Otherwise, you're basically retrospectively figuring out what went on in the past year and in what order in some cases to figure out what the reporting implications of it are. So that's been my experience, but you should be aware that in agent-based modeling, discrete time is very widely used. And for those of you who have used NetLogo, that's the sort of the standard time framework. And traditionally, it's been the framework used by Repast and Swarm, etc. It's not the only framework out there. For example, the ModGen microsimulation system also uses continuous time. And I believe the latest version of Repast, the Symphony version of Repast, now also supports continuous time as well, which is notable. Okay, so we've seen discrete space, and discrete space models depicted in continuous time and discrete time. Okay, this didn't come out too well. Just be aware that in discrete space, there are a set of different things that you do, and you can jump to a random cell. And I think the AnyLogic documentation is reasonably good on this. So you can jump to a random cell. You can find out the list of random cells. But there's certain things you can't do so easily. And I think you can't find out a list of random cells, but you could tell it, choose for me a random one from among, I misspeak. You can't say, give me a list of empty cells, but you could say, choose me a randomly chosen one of the empty cells. So jump to random empty cell. If we look at discrete space, these are the basic operators that you may want to know about. This to get the row, this to get the column, jump to a given cell, move to a cell in a certain direction, find a random empty cell, jump to random empty cell. Notably absent is find me all empty cells. You can't ask it for that list, which is too bad because sometimes you want to maintain that list. But these are key sort of primitives associated with discrete space. So any questions about that? Discrete space, very useful for representing certain types of context. In urban planning, it's quite popular for looking at neighborhood issues, et cetera, because you have lots, and each lot might depict a home or what have you, and there's some sort of exclusion going on. Not everyone can pack into one neighborhood. Yeah.
Use it in any of your health applications?
Let me think here. I've used it before in certain contexts, but I can't say that I remember a health context where we've used discrete space in a non-hybrid way. Okay. Tomorrow we're going to be looking at a central level at a bunch of hybrid models, and we do have hybrid models which use discrete space, and some of them I've given to you, many of them I've given to you, and an example here would be gridded system dynamic using AnyLogic 7. So this is a model where we have space broken up into patches. This is one that I've delivered to you. We have space broken up into patches, and that's accomplished by using a discrete space. And we've done similar things for our West Nile models to capture West Nile infection. We have a discrete space, but what's notable is within each patch, we have a system dynamics model running. And that's a very useful combination, which affords you a powerful combination of characteristics. But it's really been for hybrid models that have used them rather than strict ABMs. By contrast, my colleague Liz Bruch, she makes extensive use of discrete space models. She's in sociology, and those are of great interest there when it comes to factors involving neighborhood choice, et cetera. Okay, great question. Others?
Isn't it too expensive having all those dynamic models running inside of each cell?
Expensive in what sense? I mean, for our needs, it's not too bad. Depends on the scale of it. There is a computational cost associated with it, but in this case, the research question really motivates it because we're interested in the spread of West Nile infection over our province, and if you're going to be describing that spread using a system dynamics model, which is a very potent tool for doing that, to describe the stock of mosquitoes and the stock associated with birds and people, then you're going to be hard-pressed to make that model apply for the whole province because the province is consisting of very different ecozones and so on. So you're going to want to divide it up. And, dividing up this sort of model into hundreds or even thousands of patches and simulating it is easily viable in AnyLogic. And so it's pretty doable. Now, I would not recommend doing that with a model that consists, I would not recommend doing that lightly with a model that consists of tens of thousands or hundreds of thousands of patches. It's fairly expensive. But I will say this, that my colleagues in numerical analysis, will sometimes solve ODE, ordinary differential equation formulations of, say, the flow of electricity in the heart, which involve hundreds of thousands of coupled ordinary differential equations. And that's exactly what that is. So it's not totally prohibitive. It's just you need to be careful about what you're doing. And I would highlight very specifically choosing the time step to be appropriate for your model, because in a system dynamics model, you have to choose this kind of lockstep in which the model updates. And if it's too fine-grained, you're needlessly wasting computational power. If it's too coarse, you're not going to be simulating it accurately, and you may cause numeric errors. And so you want to you want to pick that, and AnyLogic by default uses an extremely fine time step. And it's needlessly fine for a lot of purposes. A lot of purposes are not stiff to a degree that they'll require that. Those helpful comments? Okay. Okay, other questions? Okay. Great. So we've seen discrete time, discrete space, and we are really at